Covalent bond strength. Most simply, the strength of a bond is measured by determining how much energy is required to break the bond. Specifically, to break the bond. This is the delta H of bond energy. And this is always a positive quantity. So the bond enthalpy for Cl to Cl is measured as 242 kilojoules per mole. Average bond enthalpies. Okay, this table, meaning the one right here, this table lists the average bond enthalpies for many different types of bonds, meaning between different elements and whether they're single, double, or triples. And average bond enthalpies are always positive because energy must be added to break bonds. Just think of a stick. We're going to be using Lewis dots for delta H of bond energies. So anytime you have a stick and you need to break that stick, you're going to have to add a lot of your own energy, a lot of force into breaking that stick. So if our bond enthalpies is the energy to break a bond, it's always going to be positive. We always have to add energy. And note, these are average enthalpies. Not absolute bond enthalpies. So the CH bond in methane, CH4, will be a bit different than the CH bond in chloroform, CHCl3. There's different electronegativities, different factors playing a role on how strong that bond is, but we can get an average from different compounds we've looked at. So there are going to be several ways to calculate delta H, but since we're learning about bonds and their bond energies right now, we're going to only focus on the delta H of bond energies. Which our equation for that is we have the sum of our delta H's of bonds broken minus the sum of our delta H's of bonds formed. Now I want you to use this vocabulary and only this vocabulary. When we are talking about delta H with bond energies, never use the words products and reactants. If you do so, you will really mess yourself up when we talk more about enthalpies in the future. Okay, so I want you to only think of terms of broken and formed. It is broken minus formed. So if we want to summarize this, delta H equals broken, if you're trying to remember this easily, broken minus formed. So if we're calculating this for a reaction, let's say the reaction between methane and chloride gas or chlorine gas, and these would be our products. If we want to be able to calculate how many bonds are broken and how many bonds are formed, we need a visual of bonds broken and bonds formed, which is when we're going to use our Lewis structures. So we'll start by drawing out CH4, put the least electronegative in the middle, unless it's hydrogen, then put the carbon. Put each of the other atoms around it. Now carbon had 4 valence electrons, each of the hydrogens had 4, so I had a total of 8 valence electrons to play with, 2, 4, 6, 8, I'm done. Next we'll do chlorine. I have 2 Cl's, always start by drawing a single bond between them. Each Cl has 7 valence electrons, I have 2 of them, so I have a total of 14 to play with. Fill in the outside ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We're good. These combine to form CH3Cl, put the least electronegative in the middle, which would be C. Put the 3 H's around him. And then the Cl. Carbon has 4 valence electrons, hydrogen each has 1, so now I'm at 7. Chlorine by itself has 7, so I have a total of 14 to play with. Fill in the most electronegative element with its valence electrons, and that's 2, 4, 6, 8, 10, 12, 14 total electrons, so my Lewis dot is correct. And lastly, for HCl, we have an H and a Cl. Cl has 7 valence electrons, hydrogen has 1, so I have 8 total electrons to play with, and we're good. If this had had a 2 in front of it, then you would need 2 HCl's. This would not mean these molecules are bonded together at all. It would just mean that these are separate, okay, that we have 2 of them. We do not have 2 of them, we have 1 of them. Now what we can do is calculate. And we know that we need delta H equals broken minus formed so you have 2 options here. You can either just calculate saying that every bond here was broken and every bond here was formed, and that's fine. Takes a little bit longer because you're going to have to be counting every single bond, but you will get the exact right answer. Or if you want to wait for a second and actually look at them and try and decide, okay, well, based off of these structures, which ones were broken and which ones were formed. Well, this still looks the same here. So it doesn't look like anything broke here. But this isn't there anymore. So this one and this one's broken, this one's formed. This bond no longer exists over here. So this one must have been broken. And this one wasn't in our reactants, so this one must have been formed. You can just count all the bonds, add them all up here, and just subtract them, and that's totally fine. If you want to simplify it, go and actually look at which bonds were broken and which ones were formed. Totally up to you. So if we're looking at our brokens, then I have 1. I'm going to change that size. 1 C to H bond plus 1 Cl to Cl bond. The sum of all of this minus my formed, which is 1 C to Cl bond plus 1 H to Cl bond. You don't have to write out this step, but it's a way to visualize what we're doing for our calculations. Then you're going to plug each one of these in based off of the table on the previous page. So our C to H bond is 413 plus 242. Add these together and subtract our formed, which is 328 plus 431. And our overall delta H equals a negative 104 kilojoules per mole. Negative 104 kilojoules per mole. If we look at this diagram, that makes sense. I started out here with my reactants having an energy. When I broke all the bonds, you have to add energy to break all the bonds. So I break the bonds apart. When I form new bonds, energy is released. And my overall change in energy here is negative. Started out here and went down. In fact, it is a negative 104. The last thing I want to look about with bonds is that when we're talking about length, this actually gives you our lengths, an actual number for these bonds. You never have to know these. But this is a mathematical way of looking at the fact that whenever we add a double or a triple, my length actually gets smaller. Now it's not twice as small or 3 times as small. It just does get smaller. The reason for that being, we create a higher electron density between our 2 nuclei, which means that the nuclei are pulled into that negative dense area. So it pulls those nuclei just a little bit closer if you have a double or a triple. Okay? And also remember that if it is a double or a triple, it's going to require more energy to break it. It's the same thing. If I have one stick, it's pretty easy to break. If I have 2 or 3 sticks, it's starting to get harder and harder to break. Now for our last concept here. We're talking about energy from an ionic bond formation and separation. So the heat of formation and the heat of separation for NaCl are given here. And the energy required to separate 1 mole of a solid ionic compound into its gaseous ions is called lattice energy. So we're going to talk about lattice energy and Coulomb's law. So lattice energy is when we're talking about separating a solid ionic compound. So there's positive and negative attraction that's holding it together. Lattice energy depends on the charge on the ions and the size of the ions. If we're talking about the energy that's holding them together, how much energy is holding them together is going to depend on what the charges are and the size. The stability of the ionic compound comes from the attraction between the ions of unlike charges. So stability of ionic compound is from our unlike charges. So positives and negatives. Specifically, we're going to talk about Coulomb's equation. And these are all of our units for each of the different variables in Coulomb's equation. However, you do not need to know that because we do not calculate with Coulomb's law. Okay, when you calculate in physics, you're going to use Coulomb's law to calculate things. And here we're going to use this as a logical relationship between these ions, these positives and negative charges and the distance between them. In that case, don't even think about the K, we'll just look at it as the relationship between energy and the direct relationship to our charges and the inverse relationship to our radius. So as Q1 and Q2 increase, our energy increases. So as Q1 and Q2 increase, our energy increases. In other words, they have a direct relationship. So as our charges increase, the energy required to separate them increases. Something with a positive 1 and a negative 1 charge is held together. But something with a positive 3 combined with a negative 3 is held together much stronger. So the energy required to separate 2 ions with higher charges is going to be higher. So as my charge goes up, as Q goes up, E must also go up. They have a direct relationship. Oppositely, as R increases, E decreases. So as the distance between the nuclei increases, then the energy required to separate them gets smaller. If I hold 2 magnets at a further and further distance, it becomes easier and easier to separate them. So if my nuclei are further and further apart because they have more and more electron shells between them, they're easier to separate. They're held together less strongly. Okay? So as radius increases, energy decreases, because these are an inverse relationship or an indirect relationship. As one goes up, the other one goes down. Therefore, NaBr has a higher lattice energy than KBr because my BRs are constant, so the only thing we're comparing here is my Na and my K. Na and K both have a positive 1 charge, so we're not comparing Qs at all. The only thing that can be different here are the Rs. But the difference between KBr and NaBr is that K has 1 more energy level. So that nucleus is slightly further apart, therefore it'll be easier to separate those 2 atoms from one another, those 2 ions. So applying Coulomb's law. Coulomb's law can now be applied to periodic trends from chapter 7. So what we already learned about with periodic trends, with periodic trends we use Zeph, size, and shielding. And now we can add Coulomb's law to that. So we can use Coulomb's law for several different things. We can use it to predict and explain periodic trends. We can use it to predict trends in lattice energy. We just talked about lattice energy, how much energy is required to separate ions. And we can use it for solubility. If they're being held together strongly, they're not going to be very soluble. So if you notice our solubility rules, those are all positive and negative 1 charges. None of our soluble ions have a positive 2, negative 2, positive 3, or a negative 3 charge, because the stronger the Q, the higher the E. So the stronger that charge is, the less easily you're going to be able to separate those ions, so they're not soluble in water. That positive and negative polarity on the water molecules can't pull them apart anymore. And we'll talk a lot more about that later on when we talk about solutions in chapter 11. But for now, what I really want you to be able to apply Coulomb's law to is periodic trends that we've already discussed. So right here are 11 questions that you should be able to thoroughly answer by now. And I'm going to post the answers for all 11 of these onto Edmodo over the weekend. If you can go through and answer these very well, then you're doing great on the periodic trends from chapter 7. And make sure you read through all of your notes in chapter 7, all your notes on chapter 8, and you can reopen any of your OWLs. And once they've been submitted, go into your grade book, and you can always reopen those and work through those modules. It won't change your grade once the grade is due, but you can at least go through and practice with that.